All right, we're back to talk about two more topics for energy basics. That would be work and power. Now, last year we started off talking about work. So you guys remember that work is simply the transfer of energy by a force. From one object or form to another. The transfer of energy by a force from one object or form to another. And you remember that the equation for work is capital W for work equals F times D times cosine of theta. Okay? Force times distance times the cosine of theta. Let me move that down a little bit. It's a little hard to see. There, that's a little bit better. It's still a little dark. Okay, there we go. That's a little better. So, a couple things about work. We know that, so let's see. Obviously work is W. F is the force that you're talking about. D is the displacement. This theta here is kind of interesting. Theta is the angle between the force and the displacement. Okay, if I said distance, I apologize. Force times displacement times the cosine of theta, where theta is the angle between those two vectors. Okay, and of course we know that work is measured in joules. So, one of the interesting features of this is depending on the direction of the direction of the force and the displacement and how they line up, we can have different values for the work that's done, for the energy that is transferred into or out of an object. If theta is 0 degrees, think about what cosine of the 0 degrees is. It's equal to 1. Cosine will never be above 1, and it will never be below -1. So, this cosine, if it's 1, if the value of cosine of 0 is 1, that's the biggest it's ever going to get. So if theta is 0, in other words, the force and the displacement are in the exact same direction, the work is positive and at a maximum. In other words, and it kind of makes sense, that's the biggest amount of energy transfer that you're going to get if the force is aligned with the way the object is moving. Makes sense. If theta is 180 degrees, so just to demonstrate, 0 cosine is 1, 180 cosine is -1. So that would be the work is negative. And it's the biggest it can possibly be, and being negative. Finally, if theta is 90 degrees, no work is done. Work equals 0J. Okay? So, and if it's anywhere in between those, so if it's from 0 to 90, we just know the work done is positive, but it's not at a maximum. If it's from 90 to 180 degrees, we know the work done is negative. Energy is flowing out of the object. Positive work, oh, actually, I'll write that down. Our convention, what we usually kind of assume, is that work done on a system or object is positive. What that really means, what it relates to, is that energy is transferred in, or the energy increases. Okay, so if you're doing work on an object or system, we count that as positive. That's increasing the energy of that system or object. One important note is for us to always note what force does the work. Okay, you should always be paying attention to what force is actually doing the work, and you should label that when you can. What we're going to take a look at now are some just very basic examples of how work done, or the transfer of energy, affects things like kinetic energy, gravitational potential energy, elastic potential energy. So let's first look at work and kinetic energy. So let's say that you push an object to get it moving. If the object is not moving and you push it, so now that it is moving, what have you done? You've increased its energy. Specifically, you've taken its kinetic energy from 0 and now it is some positive number. So whatever work that you've done, whatever energy you're transferring into the object, goes into the kinetic energy of the object. It turns into kinetic energy for the object. So increase in energy. In other words, work equals delta K. And this is known, it has a name, as the work kinetic energy theorem. Okay? And I guess I'll just say that this is the work done. I'm going to put WA for work done by applied force. Is assuming that it's your applied force to get it moving. Okay? I suppose it could be a normal force, it could be a force of tension, but whatever getting the object to move, that work goes into changing the kinetic energy, as long as you're pushing it along a flat surface and there's no springs involved. The energy, where you might say, well, where did it come from? It ended up as kinetic energy. Where did it come from? Did it just get created? No. The energy was originally stored in your muscles and then was transferred to the object. So energy transferred from muscles to kinetic energy of the object. Okay? So that's a relationship, a very basic one, between work and kinetic energy. What about work and gravitational potential energy? Well, we know that Fg always, for objects on Earth, points down. And we also know that any objects that are rising, well, if the force of gravity points down in an object that's rising up, that would cause Fg to do negative work, because the force and the displacement would be in different directions. The displacement would be up, the force would be pointing down. That would end up being an angular difference of 180 degrees, and therefore the cosine of 180 is -1. You get negative work. On the other hand, if the object is falling, you get positive work. So therefore, if you make the designation that up is positive, then any work done by gravity is equal to the negative change in gravitational potential energy. Because the work done by if the object goes up, it's gaining gravitational potential energy, but the force of gravity itself is doing negative work. If the object is falling down, it's losing gravitational potential energy, but the force of gravity is doing positive work. Okay, so you see how that works. If the force of gravity is doing positive work, then the gravitational potential energy must be decreasing. Okay? Let's see here. All right, one more. The relationship between work and elastic potential energy. If you're dealing with a spring, the force that the spring exerts, okay, not the force you put on the spring, but the force the spring exerts itself, and x, the displacement as it stretches or compresses, are always in opposite directions. Okay? If you try to lengthen the spring, okay, let's say you have a spring, you're stretching it to the right, the spring pulls back to the left. If you try and compress the spring to the left, the spring pushes back to the right. So those are always in different directions. Work done by the force from the spring, Fs, is negative if the stretching or compressing is away from the unstretched or uncompressed length. So what that really boils down to is if you're taking a spring and you're compressing or stretching it away from what its normal length is under no forces, then the work done by that spring is doing negative work. If, on the other hand, the object is coming back towards its if the spring is moving back towards its unstretched or uncompressed length, then positive work is done. Back to the normal length. And our equation for the work done by a spring is a little tricky. We can't actually use this equation to figure out the work done by the spring as it moves. The reason we can't use this is because this equation assumes a constant force, and that's not the case with a spring. We know that the spring force is equal to k times x. The farther it stretches, the more x changes. And this object is and as you stretch out a spring more, that force is going to change. So this equation is an incorrect assumption. Instead, what we have to do is we have to rely on this equation. Work done by the spring itself equals 1/2 kx. Let's see, what do we want to do here? Kx naught squared minus 1/2 kx squared. In other words, if the initial position, wherever the spring is or not initial position, but if x, the amount of stretching or compressing, decreases, then the spring is doing positive work. If the amount of stretching or compressing increases, then the spring itself does negative work. Okay? And again, we can't use this equation since F isn't constant as our spring deforms, either stretches or compresses. Okay? So there's a little bit about work. We're going to have to be able to calculate the amount of work done in different situations and deal with work as being energy transferred into or out of a system, energy added or subtracted away from something. The last basic topic we're going to talk about is power. And power is actually pretty simple. It is the rate at which work is done. The rate at which work is done on an object or system. Whenever you see rate at which work is done, it usually means over time. So you can think of this as power equals the work done divided by the time. We just talked about the equation for work, which is force times displacement times cosine of theta. So you could do FD cosine theta over t. And seeing that we have displacement over time, you could even simplify this to F times the average velocity times cosine of theta. Okay? All these expressions are equivalent to one another. You pick which ones you need. The units of power are watts, which is a little confusing. It's a capital W for a unit, so you need to know the context. Are you dealing with an equation that has work in it, or are you looking at a number with a unit of capital W for watts? And that symbolizes the units of power. And last but not least, power is scalar. Okay, the direction does not matter. When we come back, we're going to take a little, very quick look at gravitational potential energy, kind of what we taught. I did briefly mention what we're going to talk about, the fact that you can put the H equals 0 line anywhere that it's arbitrary. And then to finish up our notes on energy, in some future videos we're going to look at conservation of energy for pendulums and springs. So I look forward to going over that stuff with you guys.